In mathematics, a Diophantine equation is an equation of the form P x1 xj y1 yk equals 0, usually abbreviated P x y equals 0, where P x y is a polynomial with integer coefficients. A Diophantine set is a subset S of Nj, so that for some Diophantine equation P x y equals 0, n element of S m element of n k p n m equals 0. Display style bar n in S IFF exists bar m in mathbar n caret k p bar n bar m equals 0. That is, a parameter value is in the Diophantine set S if and only if the associated Diophantine equation is satisfiable under that parameter value. Note that the use of natural numbers both in S and the existential quantification merely reflects the usual applications in computability and model theory. We can equally well speak of Diophantine sets of integers and freely replace quantification over natural numbers with quantification over their integers. Also, it is sufficient to assume P is a polynomial over Q mathbar Q and multiply P by the appropriate denominators to yield integer coefficients. However, whether quantification over rationals can also be substituted for quantification over the integers is a notoriously hard open problem. The MRDP theorem states that a set of integers is Diophantine if and only if it is computably enumerable. A set of integers S is recursively enumerable if and only if there is an algorithm that, when given an integer, halts if that integer is a member of S and runs forever otherwise. This means that the concept of general Diophantine set, apparently belonging to number theory, can be taken rather in logical or recursion theoretic terms. This is far from obvious, however, and represented the culmination of some decades of work. Matiyasevich's completion of the MRDP theorem settled Hilbert's 10th problem. Hilbert's 10th problem was to find a general algorithm which can decide whether a given Diophantine equation has a solution among the integers. While Hilbert's 10th problem is not a formal mathematical statement as such, the nearly universal acceptance of the philosophical identification of a decision algorithm with a total computable predicate allows us to use the MRDP theorem to conclude that the 10th problem is unsolvable. Examples. The Pell equation x 2 minus d y plus 1 2 equals 1. Display style x caret 2 d y plus 1 caret 2 equals 1 is an example of a Diophantine equation with a parameter. The equation has a solution in the unknowns x y display style x y precisely when the parameter d display style d is 0 or not a perfect square. Namely, this equation provides a Diophantine definition of the set 0, 2, 3, 5, 6, 7, 8, 10, consisting of 0 and the natural numbers that are not perfect squares. Other examples of Diophantine definitions are as follows. The equation A equals 2 x plus 3 y display style equals 2x plus 3 y only has solutions in n display style mathbar n when A is not a power of 2. The equation A equals x plus 2 y plus 2 display style equals x plus 2 y plus 2 only has solutions in n display style mathbar n when A is greater than 1 and is not a prime number. The equation A plus x equals b display style A plus x equals b defines the set of pairs A b display style A b such that A b display style leq topic Matiyasevich's theorem. Matiyasevich's theorem, also called the Matiyasevich-Robinson-Davis-Putnam or MRDP theorem, says every computably enumerable set is Diophantine. A set S of integers is computably enumerable if there is an algorithm such that, for each integer input n, if n is a member of S, then the algorithm eventually halts, otherwise it runs forever. That is equivalent to saying there is an algorithm that runs forever and lists the members of S. A set S is Diophantine precisely if there is some polynomial with integer coefficients f n, x1, xk such that an integer n is in S if and only if there exist some integers x1, xk such that f n x1 xk equals 0. Conversely, every Diophantine set is computably enumerable. Consider a Diophantine equation f n x1 xk equals 0. Now we make an algorithm which simply tries all possible values for n x1 xk in, say, some simple order consistent with the increasing order of the sum of their absolute values, and prints n every time f n x1 xk equals 0. This algorithm will obviously run forever and will list exactly the n for which f n x1 xk equals 0 has a solution in x1 xk. Topic: Proof technique. Yuri Matiyasevich utilized a method involving Fibonacci numbers, which grow exponentially, in order to show that solutions to Diophantine equations may grow exponentially. Earlier work by Julia Robinson, Martin Davis and Hilary Putnam, hence, MRDP, had shown that this suffices to show that every computably enumerable set is Diophantine. Application to Hilbert's 10th problem. Hilbert's 10th problem asks for a general algorithm deciding the solvability of Diophantine equations. The conjunction of Matiyasevich's result with earlier results, collectively now termed the MRDP theorem, implies that a solution to Hilbert's 10th problem is impossible. Refinements. Later work has shown that the question of solvability of a Diophantine equation is undecidable even if the equation only has 9 natural number variables Matiyasevich, 1977, or 11 integer variables Ji-Wei Sunday, 1992. Further applications. Matiyasevich's theorem has since been used to prove that many problems from calculus and differential equations are unsolvable. One can also derive the following stronger form of Gödel's first incompleteness theorem from Matiyasevich's result. Corresponding to any given consistent axiomatization of number theory, one can explicitly construct a Diophantine equation which has no solutions, but such that this fact cannot be proved within the given axiomatization. According to the incompleteness theorems, a powerful enough consistent axiomatic theory is incomplete, meaning the truth of some of its propositions cannot be established within its formalism. The statement above says that this incompleteness must include the solvability of a Diophantine equation, assuming that the theory in question is a number theory. Notes